I'm Frances Hellman. I'm chair of the physics department here at Cal, and I'm delighted to welcome you to the annual Emilio Segre Distinguished Lecture. This lecture was endowed by the Raymond and Beverly Sackler Foundation, and it was intended to bring distinguished lecturers and great scientific contributors to our campus. We've particularly focused on experimentalists for this lecture in honor of Emilio Segre, who won the Nobel Prize in 1959 for discovery of the antiproton. And so we've had a long and distinguished series of lectures for this for the annual Segre lecture, and I think our speaker today amply fulfills that great tradition. So it's a great pleasure today to be able to introduce Professor Blas Cabrera, who is the Stanley Wojcicki Professor of Physics at Stanford University. He was born in Paris in 1946, did undergraduate work at the University of Virginia, got his PhD at Stanford, and stayed there as a research associate and eventually became a full professor. He has been given the Stanford the Dean's Award for Distinguished Teaching, served on the NSF Council for Cosmology. He's a fellow of the American Physical Society, and a little bit dear to my heart, has been chair of the physics department at Stanford, so we can commiserate over the joys and tribulations of that position. He gained notoriety, where I first knew of his work was in the search for magnetic monopoles, but it's the work as the leader of the cryogenic dark matter search that distinguishes him today and is what he'll be talking about today. I'm delighted that he is here to tell us about his direct detection search for dark matter, as well as some of the others that are happening all over the world, such as GLAST at Fermi and accelerators like the LHC. He's going to share with us what these experiments mean and their findings would mean for our understanding of dark matter and the structure of the galaxies and the universe. Couple of personal notes, which is kind of fun. If you Google Blas Cabrera, you'll find that there are several physicists of that same name. He is the third generation of great physicists. He is the grandson of Blas Cabrera Felipe, who worked on the magnetic susceptibility of rare earths in the early days of quantum mechanics, when they were trying to understand where magnetism even came from. He is the son of Nicholas Cabrera, and with that where's Buford? Is Buford here? Buford's right here. Buford, our own Buford Price, was a graduate student with Nicholas Cabrera. So Nicholas Cabrera was also a condensed matter scientist working on, I'm forgetting what area of condensed, sorry? Theory, condensed matter theory. So Blas also started off as a condensed matter person, and so on an entirely personal note, when I was young, just ending my postdoc experience, was interviewing for jobs all over the place, and was interviewing at an East Coast university, and was told at the end of my entire days of interviews that what they actually were looking for was a condensed matter person like Blas Cabrera. And the irony, of course, there is the type of condensed matter physics I do is extremely different than the type of condensed matter that Blas Cabrera was doing. So I basically said, if you want Blas Cabrera, it's true, you do not want me. We're doing very, very different kinds of condensed matter physics. And so the interesting part is that he's gone on to do great things, building, I think, on the condensed matter experience, but doing this wonderful work in cosmology and searching for dark matter. And so I guess I'll finish off with, it's true, I'm absolutely no Blas Cabrera, but we both have been chairs of two of the greatest physics departments in the world. And with that, I will turn the platform over and we can hear about dark matter.
Thank you. It is a great pleasure to be here, and it seems like a long ways. It's just from across the bay, but I also very much feel like bringing coals to Newcastle, because much of what I'm going to describe, there have been enormous contributions here from the physics and astronomy departments in Berkeley, and also LBL. So I'm going to remind people why it is such an amazing things have been learned about the cosmos, and many of the contributions have been from people right here in this room and at this institution. I didn't know Emilio Segre personally. I did know many of the others at LBL, including Louis Alvarez and Ron Ross, as you'll see when we talk about CDMS. He was one of the early members of CDMS. And then I also wanted right off the bat to talk about Bernard Sadoulay, who's been a close colleague for many years. In fact, the CDMS experiments, cryogenic dark matter experiments, that I'm going to spend part of the time describing, arose from 3-institution collaboration, Bernard here in Berkeley and LBL, myself at Stanford, and then David Caldwell at UC Santa Barbara. And then during the 90s, when he headed the Center for Particle Astrophysics here in Berkeley, that made huge inroads into cosmology in a broad way. So there's remarkable credit for much of what you're going to see here in Berkeley. So let me move forward. So in one slide, I'm going to try to give a flavor for our current view of how the universe arose and what's going on. And it's a remarkable picture which has come about through many, many detailed measurements and really interesting theories. And we used to, prior to the early 80s, talk about an expanding universe. And in fact, I'm going to, in this talk, go back and remind us about some of the last century and a half of work that's led to the current view we have of the universe. By the 1980s, we all believed the universe was expanding. It started from a Big Bang. And there were starting to be problems because there are many particles which we believe should exist, but we weren't seeing. And one of the inventions that occurred in the early 80s was a theory called inflation, in which we could explain why particles such as magnetic monopoles, that I'll tell you a little bit more about, that's how I got started in the dark matter field, could exist but still be sufficiently low density to have avoided any detection. And it turned out that that inflation proved to be very successful because it explained many other things we didn't understand. For example, why does the universe look so similar in different directions when we look out into the cosmos? And it appears it was all once in thermal equilibrium or in contact in causal communication. Inflation allows that to have happened here. And then after the inflation phase, everything we see today in the universe had once been in communication and thermal equilibrium. So as the universe expands then from this post-inflation period, first of all, particles that can exist do exist because they're created in interactions in this very energetic hot period. As it continues to expand, the universe cools. At about 1 second, we have big freeze out where the quarks begin to condense into the individual nucleons. And as we continue to cool, by the time we reach 300,000 years, that's the point where hydrogen becomes neutral. So when we calculate from this early Big Bang phase, roughly 3/4 of the universe is in hydrogen, roughly 1/4 in helium, and all of the other light elements have incredibly small densities in the parts per million kind of level. So at this magic point of 300,000 years, the electron attaches to the proton and hydrogen is neutral. Before that time, the universe was a conducting plasma of charged particles, electrons and nucleons. After that time, it largely becomes transparent because it's neutral and light can pass through without scattering. So the CMB, and I'm pointing here to the W map of what the fluctuations in the cosmic microwave background look like. In a very real way, those fluctuations are, we're able to look back through the universe at the surface of last scattering. This is where the universe first became transparent, and see what kind of structure resides there. And there's just been remarkable advances over the last several decades, and those data, I'll tell you some about that. And then once this neutral hydrogen formed, the fluctuations that we see in the cosmic microwave background started to gravitationally grow. So where you had an overdense region in the universe, it became more and more dense, and an underdense region in the universe became less and less dense. And that was the structure formation. The first galaxies formed. And then as time went on, we had galaxy mergers occurring. And throughout, there was a net expansion of the universe in which the galaxies were all moving further and further apart. So this is the Hubble law, as was discovered about nearly 100 years ago now, that every galaxy appears to be moving away from us, and the further away it is, the faster it appears to be moving. And that's understood in a very simple basis, that if we have dots on the surface of a balloon, as the balloon expands, all the dots appear to be moving away from each other. Further the dots are apart, the faster they appear to be moving. I'll go through that. And then we enter the modern epoch. And then the most interesting recent discovery, which has occurred over the last decade and a half, and for which Saul Perlmutter has won the Nobel Prize here at Berkeley, is that the universe is actually not slowing down in its expansion, but in fact is speeding up in its expansion. Okay, that's kind of shown here in this wiggle going to wider range. And so this is the advent of what's called dark energy, that the volume of space itself possesses an energy, and that energy is tending to cause the universe to accelerate in its expansion. Largely unexpected, and but now very well verified, and the Nobel Prize awarding indicates just how well verified that's been and how accepted that is. Okay, so let's go through some of these things and a little bit more. And first of all, I wanted to go back and look at reflecting giant telescopes, which have really been the basis for much of what we've learned about the universe. And I always loved this 48-inch brass telescope built in 1789 in Britain. And I don't know why you'd build a telescope in Britain. I actually spent a sabbatical at Oxford in the early 90s, and I think I saw the full moon on one night. But I think it's because that an astronomer in Britain would be able to spend lots of time in the local pub, waiting for that night. But this was some of the first observations of the spiral nebulas, which they had no idea what they were. In 1845, a 72-inch Newtonian refractor was used in much more detail, and many spiral form of galaxies were observed. We had no idea what they were, but we began to see the structures. And those structures are not, we don't see them because they're small, we see them because they're dim. So many galaxies, including Andromeda, are larger than the full moon. So if our eyes were sufficiently sensitive, we'd easily see them in terms of their angular size. But they're so dim that it takes a large telescope to collect enough light to see it relative to the background. The 100-inch at Mount Wilson was very important. This was used by Hubble to show that galaxy distances and the expansion of the universe. So for the first time to show that galaxies were in fact a large distance away from us, not within our own galaxy. That was a huge breakthrough. And then secondly, that when you looked at more distant galaxies, they appeared to be receding from us. So the way to interpret it was an expansion of the universe. As an experimentalist, I love technologies, and one of the major breakthroughs in reflecting telescopes was the invention of luminized aluminum surfaces, which produced very high reflectivity. And then subsequent, there were many, many coatings devised to have those aluminum surfaces last for long periods of time and also have anti-reflection. The Palomar, for a long time, the 200-inch on Mount Palomar was the mainstay of information. And in more recent times, well, actually, let's go through the Hubble. One of the things I want to highlight in the discussions tonight is that everything we know has come on very, very detailed measurements that were made. And so this is the theme of science, that we learn things because we go out and make measurements, and then test theories go back and make more measurements, and when multiple scientists observe the same thing over and over again, it becomes to be considered a fact or a part of the body of what we call science. And that process has been so successful, doesn't matter what you believe. If someone else can repeat the experiments, then we consider it science. If you can't repeat the experiments, it's not science. Right? And so in the sense of how was it that Hubble found that the Andromeda galaxy was a distant galaxy similar to ours, but much further away than anything in our own galaxy? And he was able to identify, so here's Andromeda with the two satellite galaxies. And again, the full moon is about that big. So this is about 6 times the diameter of the full moon. Very large object. You can see it with your naked eye at a dark site when there's not a lot of city lights and the moon is not out. And he was able to identify individual stars in Andromeda, which actually are so-called Cepheids, and they go through a periodic oscillation of intensity. So you can see this is magnitude 19, magnitude 18. The magnitude scale gets brighter as the number gets smaller. So it changes through about 1 magnitude. That's about a factor of 2.5 in intensity. And notice here, this is days, so this takes about 25 days or so to go through a period, and then you get another period. And so he looked at a number of different stars. You can imagine how many detailed measurements needed to be made over and over again, night after night, to actually get these data. And he was able to show that these points of light in this distant object had the same shape as Cepheids in our own galaxy. But the Cepheids in our own galaxy are much brighter because they're closer. So we know when something is twice as far away, it's 4 times dimmer. And so he was able to directly show that a Cepheid, where the period between these oscillations is directly related to its intrinsic brightness, could tell him that this object, the Andromeda Galaxy, is much further away than any of the objects that we're seeing in our own galaxy. So that was dramatic evidence that this is an island universe similar to Milky Way outside of the Milky Way. We continue to do that today. The Hubble telescope in space can do this much more precisely to much greater distances. So this is a further out galaxy in which a Cepheid is being mapped out here, and you can see the intensity variation even just in the pictures. And so that same technique is being used even today, and Hubble was used in this way rather well. Now let's just briefly go through how it is that the expansion of the universe was discovered. And again, what Hubble did is he measured the many different galaxies, and he was able to measure something called the redshift. And here I've shown in schematic where you see a rainbow smearing out of colors from a distant galaxy. Stars in our own galaxy also have colors. And the stars and galaxies have fingerprints associated mostly with hydrogen. Hydrogen has many different discrete levels of energy which show up as absorption lines. That's why they're black lines here. And when you see this fingerprint shifted, all of them shifted in the same direction by the same amount, that's a redshift. And that's the same effect as happens when you're standing at a train station and the train whizzes towards you. It sounds high-pitched, and if you're at, say, an express train which is not stopping at your station, zips on by, it goes as it passes on by. And that's very real. It's that the sound waves when the train is coming towards you are a little bit closer together because each one is emitted a little bit closer to you. And on the backside, each one is a little bit further away. And so that changes the frequency. And the same thing happens with light, that when galaxies are receding from us, they are redshifted. All of the frequencies are shifted towards the red end of the spectrum. And this is the original data of Hubble, which doesn't look too convincing in terms of a straight line, but he said, yes, this is showing the universe is expanding. And notice that this is now over a distance of about 2 million parsecs, and that's about 6 million light years. And then this is the kilometers per second in this direction here. And then here, what we have is much bigger distance. So instead of going to 2 megaparsecs, this is 500. And so that's about 1,500 light years away. And now you're beginning to see that the points are much closer to the line because you've gone out far enough so that the expansion of the universe dominates all of the local motions of galaxies, such as the ones close to us. So this all came about from that. I wanted to say a little bit more about spectroscopy because I'm actually teaching an introductory astronomy class at Stanford this quarter. And I thought about how is it can I introduce spectroscopy, because almost everything we know about the night sky actually comes from the spectrum, not from the images that you see in Hubble and other telescopes. And so this is an image taken with a Canon digital camera through a 5-inch telescope that big, pointed at one of the bright stars that's close to us, Altair. And it was very surprising to me that you can clearly see the Balmer series lines. So you can see them here, these dark bands that occur in this image. And this is the primary star, and this is the first order through a grating where it breaks it up into colors. And because the digital camera has colors, you can see the different colors. And then you know exactly what the wavelength is from the distance from the primary over to here. And then here's just a converting the digital information to a graph, and superimposed on it are the Balmer series of hydrogen alpha, beta, gamma, delta, etc. And it was very impressive how easy it is to see those. These features here are actually atmospheric absorption in our own atmosphere. So you can begin to teach people just visually through a 5-inch telescope the spectral information that's available locally, and then that, of course, imprints on distant galaxies as well. Okay, and then I talked about the expansion. Let's just go through that one more time, that if we look at 3 galaxies that are close together when the universe is closer to the beginning of its expansion, if the entire system is expanding like a balloon, they're all moving further and further apart, and when it's twice as far away from you, the distance it appears to be moving away from you is twice as much. So the slope of this line is the apparent velocity away from us. And all of these objects are standing still locally. Okay, it's the thing that's causing the expansion is the entire space is expanding, not that they're moving relative to the space. So that's the important point. And then in addition, the fact there was such scatter in the nearby objects is because they are also gravitationally attracting each other. So they have relative motions relative to the local space, and those relative motions remain the same. So as you go further and further out this curve, the scatter around the line is a smaller percent of the total. That's why when we looked a long ways out, the Hubble law was much better, much less scatter. Okay, so what's the next step in the story? Zwicky, and I actually like this picture better than the one that you usually see of him, was at Caltech. And in 1934, he was the first to make detailed spectroscopic measurements of the Coma cluster, which is 1,000 galaxies which are clearly gravitationally bound because they're in the same region of the sky. So they're gravitationally bound in a cloud. And he was able to measure for each one how fast it was moving towards us or away from us, the redshift. And then by looking at the difference in redshift compared to the average redshift for the whole cloud, he could tell what their relative velocities were relative to the center of mass. And what he found was that he needed something like 10 times more total mass to explain the fact this was gravitationally bound. They were moving too fast to be explained just based on the mass of the stars and the gas that make up the stars. Okay, so that was quite an accomplishment. In that epoch, there were lots of people who said, well, maybe we don't understand the mass of stars and galaxies, so there are lots of places where we could be making systematic errors, so let's not make too much of this. The next step in the story can be summarized in the early 70s, and this is Vera Rubin, who, with a very sensitive new spectrometer, began to make spectrographic, and notice that I keep coming back to spectra. Almost everything we know is from measurements with spectra. Spectrographic measurements of each individual galaxy. So instead of looking at the velocity of the entire galaxy, she was able to put a slit across a galaxy, and this is a more edge-on galaxy, and then to look at the redshift on one side of center versus the other side of center. And what we were expecting to see is a peak, and then that all the velocity should be going back down towards 0 on either side. Sort of like the Kepler orbits around the planetary system in our own solar system. Okay, we know that as you go further and further out in the solar system, that the planets are moving more and more slowly. Let's show the next slide here. Okay, so this is my only equations, which is first year of introductory mechanics. If this were a solar system, we'd expect the dotted line. Kepler's laws say that the velocity of an object around the sun falls off as 1 over the square root of the distance from the sun. And instead, what we see for galaxies is they don't behave like giant solar systems, as we might expect. Instead, we see the velocity going to a flat curve, flat rotation curve as it's called. And the question is, who ordered that? Where did that come from? And it turns out that if you assume that the mass contained within a sphere increases proportional to the radius, then you'll see the velocity as a constant. So this kind of data is consistent with a mass that's increasing proportional to radius, and that means by the time you've gotten out to a factor of 3 or so beyond where you see no more stars, that you've got something like 10 times more dark matter, as it's been called, than luminous matter. And there are lots of suggestions that maybe we don't understand gravity on these large scales. Maybe we need to modify gravity. And there's been lots of work in that direction over the years as well. What I'm going to, well, first of all, let's go through the expansion scenarios, and I'll come back to the point. So what happened then in this early universe when we started in the expanding universe and the regions that were slightly overdense grow to more and more dense regions? So this is a, let's start it back one more time. This is one where we're watching the universe expand. Okay, so it starts from a very small ball, increases in size, and the structure in the universe gets more and more pronounced as time goes on. And these are from numerical simulations that have been repeated in many, many different locations, and in which the contributors here in Berkeley have made major contributions as well. This is looking at it from what's called a co-moving frame. This will go through a cycle. Initially, at the microwave background epoch, we have very, very small fluctuations in density. If we follow a cube that is increasing in size with the expansion of the universe, what we see is the places that are overdense continue to become more overdense, and the places that are underdense become more and more voids. And the yellowish spots are places where we've gotten sufficient density that the baryonic component, the atoms in this flow, condense and form galaxies. So that's where we expect the galaxies to form. And this scenario of expanding universe with small fluctuations at the time of the cosmic microwave background leads to this structure. And when we take surveys of the sky, each point in this survey corresponds to a galaxy, and the angular position of the galaxy on the sky is in this direction, and the redshift is in the dimension going outward. So because Hubble showed us that we can get a measurement of how far a galaxy is from its redshift, we can plot the third dimension in space by looking at redshift. And what we see is this foam looking like structure where we have filaments with knots between them. It looks very similar to what the numerical simulations show. And so that's quite remarkable that these images of the sky are beginning to look like what we do in the numerical simulations. Now, what are the constituents then of the universe to make these pictures hang together? And I'm now going to show you what we're calling the model of cosmology that's come about from detailed measurements from what I showed you and then the more recent measurements over the last several decades, which include the supernova as a standard candle, that there's a particular type of supernova called the type 1a, which we believe it explodes with very similar intrinsic brightness everywhere in the universe. And so if we identify those explosions and measure how, what their apparent brightness is, we can get an independent distance scale. And that allows us to look for this question about whether the universe is accelerating or deaccelerating. In a plot here in which on this dimension we have the mass, the matter density of the universe, and matter density will be all portions of the universe that condense gravitationally to form structure. And in this direction we have cosmological constant or dark energy density of the universe. What we find is that three very different kinds of measurements are leading to the same common intersection point in these two-dimensional plot of about 1/3 of the universe, 0.3, being in matter density. That's all the parts that form atoms and form structure. And about 2/3 or 0.7 being in this cosmological constant or dark energy piece. Okay, and this is the supernova data that lead to this contribution. The CMB, looking at the fluctuations that we see at the 300,000-year-old universe, shows solutions that are along this band. And finally, looking in detail at clusters of galaxies and measuring the total mass of the cluster by the deflection of the light from background galaxies, where you can see that they're distorted because of the mass in the cluster that you're looking at. That gives you an independent measure of the total mass of the cluster. All three of those in very different directions in this two-dimensional plot intersect at the same point. Okay, and so now, and then let's see. So this is Saul Perlmutter et al. Contributed in a major way in the microwave background measurements. Paul Richard and now Adrian Lee and many others here at Berkeley and LBL are contributing. Weak lensing, Tony Tyson and others, and also this is related to the macho experiment work that Berkeley had quite a bit to do with. So major contributions from people in this room. The microwave background is worth talking a little bit more about, and I was very struck by the progress in measuring the microwave background. It was first identified in 1965 by Wilson and Penzias, and so that's what we call the monopole term, the fact that everywhere we look out in the sky there seems to be the afterglow of the Big Bang, and it's about a little under 3 degrees Kelvin. And 0 degrees Kelvin is 459 degrees below 0 Fahrenheit. So that's pretty cold out there in the sky, but that's not zero. This is still a finite temperature. And it's an incredibly accurate black body, as we call it, that if we have a body at a constant temperature, it radiates a very well predicted spectrum. And that's exactly what we saw with COBE. And this was first identified in 1965 and then shown to be a black body to very high precision in the satellites early 90s. Okay, the next step was that when we start looking for ripples, for variations from uniform in this constant temperature, we find that the next biggest thing is 1,000 times smaller. So notice this is now about 3 millikelvin, 3/1000ths of a degree. And it is a dipole in which in this projection, this is the North Pole and the South Pole. And so what this means is that our reference frame is moving through the average microwave background photons in a particular direction. And so that's the particular velocity of our galaxy and solar system is moving at about 300 kilometers per second in a particular direction. And if we subtract away this dipole term, finally, at 2 orders of magnitude smaller, down in the about 10 microkelvin regime, incredibly difficult work to get to be able to detect this very, very small signal. This is the galactic plane, by the way. The coordinates are such the galactic plane is through the equator of this projection. And COBE was the first satellite to actually demonstrate that these fluctuations were real and beyond just statistical fluctuations. So that was the first observation that there were really warm and cold spots on this surface that was the surface of the universe when it was 300,000 years old. Okay? And again, just you're measuring 10 microkelvin, and even today they're moving to even smaller temperature measurements as we measure more and more details about the microwave background. And in many ways, the most precise information we have about the constituents of the universe today come from the wiggles. And what we're plotting here is the angular scale. So when 2 objects on the sky are about 2 degrees apart, that is this peak. So that corresponds to this many wiggles around a circle. And then when you get to 1 degree apart, you're here, half a degree apart. And the green line is a prediction from theory as to what these so-called acoustic oscillations should look like. And so this is you can just calculate in the early universe what response you should have from different constituents, dark energy, dark matter, and atoms, which are the 3 major constituents we'll talk about. And each one of these wiggles then puts very strong constraints on exactly how much of those constituents there can be. And let me show the pie chart here rather than going through that in detail. So here is our best shot at what are the constituents of the universe today. And 73% is in the form of this expansion term that's causing expansion called dark energy. And so that is what Perlmutter et al. Have recently won the Nobel Prize for, the realization the universe is accelerating today, whereas people thought it was deaccelerating previously. Everything else, dark matter and atoms, correspond to matter density of the universe. And that's important because all of these constituents are the ones that clump gravitationally and therefore all of structure that forms in the universe has to have come from that sector. Okay, and because the dark matter dominates, there's about 23%, whereas the most there can be in atoms is about 4%. So all of the stars plus the gas that makes up the stars is less than 1% of the universe. So everything we see out in the night sky corresponds to less than 1% of the universe. And there's about 3% that's in cold atoms, and we believe we know where that is, probably in the filaments that haven't yet condensed enough to form galaxies. And then 23% from the arguments of WMAP and others cannot be in the form of atoms. Okay, so what is it that's this 23%? That's what has I have been looking at for the past 30 years, and there are about 30 or 40 major experiments worldwide to try to determine. So mostly I'm going to talk about the hypothesis that it's weakly interacting massive particles. Now, why do we believe that it's not a modification of gravity that is producing this apparent dark matter component? And for me, the most convincing argument against that comes from what's called a bullet cluster. So these are two large clusters of galaxies, a large one and a semi-large one that moved through each other about 500 million years ago. And we're able with this cluster to make three independent types of measurements. We can locate the galaxies visually. We can locate where the mass is through the distortion of the background galaxies, the way that I described making the mass measurement of a cluster of galaxies. That's the purple. So where the purple is brightest, that's where most of the mass is from the distortion of background galaxies. And third, we can measure where the atoms are because they emit X-rays. Most of the atoms are in the form of gas, and that gas has bumped into each other. So that was originally spread out in one galaxy. As one galaxy passed through the other, the gas bumped into itself and formed the shock wave, and the gas was mostly separated from the center of mass of the two galaxies. So most of the atoms are in this intermediate region and have been shifted from where most of the mass is. Okay, and so for me, that's the most convincing argument that what we're seeing is a real particle and not some modification of gravity, because this is a non-local effect. You'd need to have a really weird gravitational theory to propose such a non-local effect. Okay, so then what is the particle? Oh, and let's say what kind of experiments are we going to do in the laboratory. Galaxies have grown from many coalescences of smaller galaxies into bigger ones. This is sort of the tree of a typical galaxy like the Milky Way, in which many smaller structures coalesce together to form the bigger structure. So here's two structures. We know that the Milky Way and the Andromeda Galaxy will go through such a merger in about 1 billion years, 500 million to 1 billion years. They're on a collision course with each other. And what happens afterward? The solar system may be ejected. It may become an elliptical galaxy, or it may become another type of spiral galaxy. And these simulations, which have to have the dark matter particles in them, give us ideas of what the distribution of velocities is for dark matter in the vicinity of our solar system. That's why this has always been useful for us. And the dark matter on the average is standing still and the galaxy's rotating through it. And that's because the dark matter didn't collapse and condense the way the atoms and baryons did. And they spun up when they condensed and collapsed to the middle. And the sigma, these are bell-shaped distributions in each of the 3 dimensions, with a sigma standard deviation of about 200 kilometers per second, which, by the way, is the same as the velocity of the solar system around the galaxy today. Okay, so our solar system is moving through the average dark matter at rest with about 200 kilometers per second. That always leads to the most exciting experimental techniques being ones in which you could tell which way the dark matter particles were going. All right, so in this plot, I'm going to do all of particle theory on one graph. All right, so these are the 4 known forces of nature. Gravity, which is the weakest, it's the one that was known first because everything gravitates and adds together. The strong force holds the nucleus together. The weak force is responsible for radioactive decays, and the electric-magnetic force was the second one to be discovered. In fact, electricity and magnetism separately and then unified by Maxwell in the 1870s. And very successful unification occurred in the early 80s, where we now know in one theory how to describe electricity and magnetism and weak interactions, and so-called electroweak unification. And the predictions of that theory is that there exist particles called the W and the Z that are the intermediaries between the weak force and electricity and magnetism. And those were discovered by UA1. Bernard Sadoulet was a member of UA1 in the early 80s. And very convincingly showed that we understand electroweak unification. That was so successful that rapidly the suggestion that we unify all the forces of nature, initially through grand unification at about the 10 to the 14th GeV scale. A GeV, by the way, is about the mass of a proton, so this is 14 orders of magnitude greater than the mass of a proton. The highest energy accelerators are at about 1 TeV now, that's the LHC. So we have some orders of magnitude for Earth-based accelerators to get to this region. For me, the place I came into this is that grand unification necessitates the existence of magnetically charged particles. And there was a suggestion in the late 70s, 79, that maybe magnetically charged particles, which must be 100 times more massive than this unification scale, making them about 10 to the 16th GeV, are the dark matter. So that got me interested. You know, dark matter is a pretty interesting problem, and if you can detect magnetically charged particles, which we thought we could do, then that's a way to look for what might make up the dark matter. And then these unification theories were so successful that really including gravity at the Planck scale has led to the theory of everything, or string theory. And I'm not going to be able to go into details, but it's an incredibly powerful combination of all of the other theories we know into a mathematical structure that there's an immense amount of work going on. By the way, just to today we're at about 10 to the minus 11 GeV is the temperature of this microwave background. And so in some sense, the accelerators are at about the geometric mean between this scale and that scale down there. Okay, and I don't have time to say much. Monopoles, just for a quick introduction, that all of the charged particles we know about in nature are electrically charged, and magnetic fields are produced by running them around a circle to produce magnetic fields with no ends or beginnings. So these have curl but no divergence. And the question is, Maxwell's equations certainly could have particles that are sources or sinks of magnetic field, and when you ran them around in circles, you'd produce electric fields with no divergence. And so that's one of the candidates for dark matter, and I actually put it way up here. This is a plot of all known candidates which you would like to have exist for some reason in particle theory, and the monopole is up here. Red means we've largely excluded them. Monopoles for a number of reasons, but inflation is the primary one. Inflation is so successful at reducing the density of monopoles that they really should be impossible to see in today's universe. But we believe they exist because they're necessary in the unification theories, which are the most elegant theories of nature that we have. So the two candidates which are most likely are the neutralino, which is a subset of these weakly interacting massive particles. That's this red circle. And the other one that's being looked for today is the axion, which comes in this region here. The axion has strong reasons for existing, that it's the most elegant solution to why the strong force obeys CP invariance, whereas the weak force doesn't. And why is it that most experiments today looking for dark matter are looking for WIMPs instead of looking for axions? And by the way, the other thing I won't have time to say anything else about is that there are candidates which would be very difficult for us to even imagine a way to see, for example, the gravitino or the axino. So there are lots of constructions where you can have dark matter in the form of a particle where we don't yet know how to look for it. Okay, so the reason that most experiments are looking for WIMPs is come to be called the WIMP miracle. And that is that if you have weakly interacting massive particles that are neutral, so they don't have any charge interactions, that you can calculate how many of them there should be today based on their annihilation cross-section. What's the probability of a particle-antiparticle annihilating? In the early universe, when the densities are very high, you'd have lots of annihilations. And then as the temperature cools and comes below the temperature to produce the particle, you should get an exponential decrease in the density of the particle. Now, what shuts off that exponential decrease is the universe is expanding. So there comes a time when the average distance between particles shuts off the probability of them finding each other again. And interestingly, when the annihilation cross-section is large, more of them decay away before that expansion occurs, and you end up with a large density. And when the annihilation cross-section is small, they go further down this curve and end up with a small density. And so there exists a balance point where the relic density we see today is tied to an annihilation cross-section. And the miracle is that that annihilation cross-section is very close to the weak interaction scale. So it says that cosmology, independent of particle physics, is pointing to the same energy scale as the weak interaction scale responsible for the W and the Z, and possibly the Higgs just around the corner at the LHC. So that's why there is such interest in this model, because there's kind of a natural way to explain what makes up the dark matter in the form of these particles. If this hypothesis is correct, then there are multiple ways to look for it. So here is a picture of our galaxy embedded in a halo of dark matter particles. And by the way, the term halo is bad because it's not a ring around the galaxy. It permeates all of the galaxy, the highest densities at the middle, but it's just much puffier than the galaxy, so it spreads way out. And there's the LHC, which could produce particles. And then there are indirect detection experiments like IceCube, Buford Price here, member of the IceCube team, HESS that looks for gamma rays interacting the atmosphere, and GLAST Fermi that's a observatory looking for gamma rays. These could see annihilations of WIMP, anti-WIMPs, either in the sun in the case of IceCube, or in the galaxy producing gamma rays in the case of these two. And then the other way is what we call direct detection, that's to look for recoils, rare recoils occurring in detectors that are carefully shielded in laboratories on the Earth. Okay, and there is a complementarity between these two approaches, which is that we plot the cross-section in this direction, which is how many events should occur per kilogram per day, versus the mass of the particle in this direction. And this is 10 times the mass of the proton, 100 times, and 1,000 times. And in this plot, each one of these curves, this is our most recent limit, which excludes all theories for particle masses and interactions above that. This is the Xenon 100 recent limit that excludes everything above that line there. And the experiments that we are undertaking, this is the one that's currently going to run in the Sudan mine, 10 kilograms. We're working on the 100 kilogram and possibly a ton scale. The same theories of supersymmetry that produce candidates for WIMPs in this plot should also be accessible to the LHC. And this is an inverse femtobarn at the LHC, where the co-annihilation and bulk regions of supersymmetry, which are green and red here. So notice that it is particularly sensitive at those regions. Direct detection is very good at the bulk and somewhat more difficult to reach down in the co-annihilation. And the Higgs funnel and focus points, which are that region and this region here, again, focus is easier with direct detection and more difficult LHC. So there's complementary regions. There's also about a 300 GeV range where if the particle is more massive than that, you won't see it with the LHC because it can't produce it. Okay, so let's see. I'm going to have to go faster here. So this is how it is that we looked for dark matter particles in the laboratory. The prediction of weakly interacting massive particles is they scatter elastically off nuclei. very, very small probability of scattering off electrons. Most of the backgrounds in the laboratory are produced by gamma rays that produce recoiling electrons. So our detectors are designed to be able to discriminate between recoiling nuclei and recoiling electrons. And there's an incredible ingenuity that's occurred in the field over the last several decades. And we use all possible ways in which radiation and particles interact with matter. So the things that happen are ionization, where electrons are pulled off of atoms, scintillation, where the recombination of those electrons emits photons, and phonons, or heat, which is eventually all the energy ends up heating up the detector. Okay? And so in the case of CDMS, we simultaneously measure ionization and this heat. And let's look at one other experiment, Xenon 100, which just recently announced the most sensitive limits. They're simultaneously looking at ionization and scintillation. Okay? And there are experiments that some only look at one, like CREST just looks at heat, and others just look at scintillation, like Deep and Clean, XMass, and so forth. So there's incredible variation in the ways in which the experiments are set up. I love this plot. This is the Moore's law for dark matter searches. Starting about 1986 or 7 are the first papers that were written, Homestake and Orville, and down to the present. Notice in the future we all think we're going to go faster than we do. So I'm guessing we're probably not far from this. And every 5 years we do 1 order of magnitude improvement in sensitivity. So if we follow that along, we'll get down to this 46, 47 and through this next decade. And there are many contributions. These are the CDMS contributions. Here, this is Xenon 100. Here and here, the 2 most recent results. And this is our next 10 kilogram experiment and 100 kilogram experiment here. All right, so in the last few minutes, I just want to give you a sense of what our experiment looks like. And I like this picture because we're in the mine, half-mile underground in northern Minnesota. There's Bernard, and here's me. We look much younger at that time. And the collaboration has grown. It's about 100 people today. This is a recent collaboration picture with Bernard and myself looking much older. And this is the institutions involved. And we are going to be moving from this half-mile underground site at Sudan. And this is the mine head at the Sudan mine. It was first started in 1884, so it's a remarkably historical site. And there are tours that go through the mine during the summer. It's at this elevation. Why do we go underground? We go underground to reduce the muons coming from the atmosphere, which produce backgrounds. And the deeper we go underground, the more we can reduce those backgrounds. And in the next phase of the experiment, we're going to Sudbury, which is 3 times deeper, about 1.5 miles underground. And that has about a factor of 1,000 fewer muons. This is an example of one of the dark matter experiments, the CDMS. It is a cryogenic refrigerator vessel surrounded by ancient lead, and then surrounded by polyethylene, and then surrounded by plastic scintillator. So any muon that passes through this system we can tag and throw out the events. And the inside temperature of this vessel gets to about 1/20th of a degree above absolute zero. So at this very low temperature, it allows us to measure the heat of an elementary particle interacting with a large massive crystal of germanium. And this is what the detectors look like. These are fabricated at Stanford and tested here at Berkeley. This is 1 inch thick and 3 inches in diameter, kind of a hockey puck size crystal of germanium, which weighs about 0.6 kilograms, 600 grams. And this is what happens when an event occurs, that energy in the form of ionization and heat is generated at a point. It grows throughout the crystal. And we have the ability to measure the charge with these 2 channels, and the ability to measure the arrival of the heat in the form of phonons with both surfaces. And you can see that there is information imprinted as to where the event started. and we use all of that information in terms of rejecting backgrounds by identifying where each particle was, that it was point-like versus being multiple interactions. The 2 years of data that went into the most recent result were taken between 2006, 2008, and correspond to about 10 million background events that occurred over the 2 years. We did 220 million calibration gamma events and about 2 million neutron calibration events throughout. And that allowed us to understand the way in which the detectors behaved in great detail. And this is one event that occurred out of those 10 million. So here is the phonon signals and the charge signal, all the others quiet. So if WIMP should not interact with more than one detector at a time. So just looking at single events is what we're after. We took all of those events, 10 million, and we were able to reject all but 2 from the acceptance window. Green are nuclear recoils from the neutron calibrations. And we believe, or we would say the maximum likelihood analysis tells us that those 2 events are more likely a background of surface electrons than they are an indication of a WIMP signal. Okay, so that's our statement on those 2. So we're looking at it as setting limits of not seeing WIMPs at that level. And this is the science paper which showed the limit set by those data in a similar plot to the one I showed you before. Okay, so what next? So the next step is that we need to go larger. And so tomorrow, 10 kilograms of new detectors, which have been fabricated and tested here at Berkeley, are arriving at the Sudan mine in northern Minnesota. And those will produce a sensitivity in this range here, maybe a little bit lower. And we're also working on a 100-kilogram version of the experiment, and we want to put that in the Sudbury mine at 1.5 times deeper, and that should give us this sensitivity here. And there are plans for a 10 times bigger experiment that would give a reach down to about here. So that's kind of the trajectories that we're interested in. We're now sitting at a cross-section sensitivity of about 10 to the minus 44. And the idea in the future is to go down below 10 to the minus 47. There are even experiments talking about 10 to the minus 48 centimeters squared in cross-section. So let me just finish up here. So LHC has turned on and is exploring particle physics in the TeV mass range, where there must be new physics, and it may produce the particles that make up the dark matter. So that's one exciting development that will happen over this period. Many indirect experiments, such as IceCube, Hess, and Fermi, are looking for dark matter annihilations in our galaxy. And already there are interesting limits from Fermi and IceCube, which are putting constraints on dark matter. The direct detection experiments, such as ours and Xenon, Warp Coop, and many others, are looking for dark matter particles to scatter off detectors. And within this 5 to 10 year period, I tell all prospective students and postdocs that we will discover WIMPs or confirm that the favorite model for what makes up the dark matter is largely ruled out. Either way, that's an advance in science. And either way, we also have a great horse race for discovering WIMPs with all the experiments going on. So I thank you.
So thank you. So the floor is open for questions.
I have a question about AMS2 and how does that relate to this, and what are they looking for?
Say that again?
The new AMS?
The antimatter spectrometer, so that's looking for antimatter in the galaxy. And that there could be some tie in terms of an annihilation. Anti-WIMP annihilation could produce antiparticles. So there would be some source of antiparticles from that. Okay.
Are WIMPs their own antiparticle?
They could be.
Are WIMPs their own antiparticle?
Right. They could be, but the nice thing about direct detection experiments is that they will collide whether there's one type of particle. So for example, suppose there's particle-antiparticle asymmetry in the dark matter sector the way there is in the baryon sector, and atoms only come in atoms, not anti-atoms. Then they would still scatter off detectors in the laboratory, but they wouldn't annihilate. If they are Majorana particles, they would annihilate and they would also scatter. So,
What would an annihilation reaction look like?
right, and there's quite a bit of work that's been done on that, particularly for Fermi, which is looking out. Most models don't give you a sharp line, so what would have been wonderful is to have, when an electron and a positron annihilate, you get very specific 511 keV gammas. And so if you're looking with a spectrometer, you see a peak at 511 keV. In the case of WIMP, anti-WIMP annihilation, for most models that are derived from this structure of supersymmetry, you do not see a peak. There's a sort of a broad bump of energetic gammas and other particles, and the gammas are part of what they're looking for to see if there's an excess bump seen within the galaxy.
Good.
It's a very general question, but you say that in the next billion years, Andromeda and the Milky Way will collide.
Right.
So what happened in the last 2 billion years? Were there galaxy collisions that created the Milky Way?
Yes. So like I showed you in that tree, we believe there were a dozen or so significant coalescences that occurred in the Milky Way, probably with one being significantly bigger than the other, so the dominant one maintains most of its structure. In the case of many of the simulations, for example, when we have two large similar mass ones, you may end up with an elliptical galaxy where much of the spiral structure is gone and it becomes more an elliptical structure. So we're not quite sure which one of those will develop. There are simulations that have been done in terms of Andromeda and the Milky Way. Well, the bullet cluster is a cluster of galaxies, so it's like the Coma cluster, so that's many galaxies gravitationally bound in a much larger structure. So for example, the Milky Way Andromeda is part of the local group, which has maybe 3 or 4 additional galaxies that are gravitationally bound locally. And the bullet cluster is an even bigger set of galaxies, one of which has gone through another collection of galaxies. The reason that one's important is because we have enough background galaxies, since it's a big enough object, to be able to independently measure the mass from the distortion of the background galaxies. With Andromeda, there's not enough stuff back behind it to get an independent measure of that mass. Same way.
Right here?
How does dark matter lose energy so it can aggregate together the density?
Not easily, right?
How does dark
Right.
matter, say it again, or do you want to repeat the question?
Yeah, how does dark matter lose energy was the question. So it aggregates together. In fact, the reason that you talk about dark matter halos is because the dark matter didn't collapse to the center. The dark matter started the process of coalescing when things were at low density. And then as you get to higher and higher density, the atoms bump into each other and fall to the center of the potential well started by the dark matter. And the dark matter stays relatively puffy and not rotating very fast because it doesn't collapse into the center. So you're just looking for those rare annihilations occurring today in the higher density regions of the galaxy, which are still not compressed the way that matter has been compressed. And then in the sun, we do believe there's enough thickness to the sun, if you will, that occasionally WIMPs can be captured and then slowly wander to the center. And then you'll have an increased density of WIMPs, anti-WIMPs at the center. When they annihilate, an energetic neutrino can come out and be observed by IceCube. That's the model that people are looking at there.
So is that all the assumptions of the matters now is that all the matters are created at the beginning of the universe, as well as the dark matter?
Right.
Would there be a possibility that there are still matters being generated after?
So
Well,
the
in a
question is, could
yeah.
matter have be being created after the Big Bang?
Right, and the pictures that we're talking about do have the energy density in the early universe having been created in the Big Bang. There is, so the process of inflation, there is a rapid expansion of the universe. That expansion does take energy, and when that expansion slows down, the energy of the kinetic energy of expansion gets converted to particles. So the universe is repopulated with particles up to the reheating temperature, and that's why we don't see the really heavy particles like magnetic monopoles, because it doesn't reheat to arbitrarily high temperature, just up to enough to populate the ones we see. So in that sense, we have created particles in that epoch, post-inflation. The other comment to make is that the dark energy term is kind of proportional to the volume of space. And as the universe expands, its volume is growing bigger. And so the percent of the energy of the universe that's in dark energy increases as time goes on. Okay, so in that sense, there is a change in the partitioning of energy between dark energy and particles.
Over there.
You mentioned modified gravity versus dark
Right.
matter.
Right.
But modified gravity essentially gives you the flat curve.
Right.
So you can have both of them and it'll give you the flat curve even more strongly. How much have you...
So the question was, could modified gravity give you a flat curve together with dark matter?
Right. I mean, the nice thing about the dark matter particle model is that if you do the simplest thing, which is say, look at a gravitationally bound cloud of dissipationless particles, that automatically has the 1 over r increase in mass with distance out. So it naturally explains what you see. You could always have part of it in one term and part in another. The bullet cluster very nicely separates the atoms from what appears to be most of the mass, and so that's where I think there's a strong pointer to particle rather than needing to modify gravity.
Right here?
Yes. You explained the constant rotational velocity within galaxies as opposed to in the solar system.
Right.
In terms of the density of dark matter increasing as you go outward.
Right.
So,
No, the density, the total amount of dark matter in a sphere of that radius increases linearly proportional to the radius. But remember, the volume goes as the radius cubed, so the density is going down as 1 over the distance squared.
I see. So there's nothing clearing it out of the center.
No, it's maximum at the center, and then goes off as a 1 over r squared density as you move out. And then you integrate that, and you get something increasing proportional to radius.
Question right here.
Which are the main arguments against the gravitational theory of Einstein or the cosmological constant that has certain characteristics of the space?
Yeah, so I
Can you
didn't.
maybe repeat
Right.
that?
So the question is, what's the relation of the cosmological constant in Einstein's general relativity to what we're seeing here? It's a very good question. So I didn't go through that in detail. The amazing thing about Saul Perlmutter and company's demonstration of this expansion of the universe is that all of the data that we've looked at point to something that looks just like the cosmological constant in Einstein's theory. So it behaves in the same way in terms of the evolution that we've been able to see so far. And the surprising thing, however, is that in particle physics theories, you can set the scale of the cosmological constant. It comes naturally out of the theories. And that scale is 120 orders of magnitude bigger than what we see today. So it's the biggest experimental theoretical discrepancy that we've ever had. Okay? And theorists have toiled very hard to try to understand that, and the closest we've come is the very unsatisfying anthropic principle, where the argument is that only universes that have a very, very tiny value for the cosmological constant are interesting, that structure can't form in the ones that have the natural scale, and that if you have a sufficiently rich set of possibilities, that there will always be some universes with sufficiently small value of cosmological constant to make interesting structures and to have individuals and beings in them that ask the question of where we came from. Okay, so it's a little bit difficult as an experimentalist to talk about the anthropic principle, but there is a very large body within theory that is pointing to that. So it's still Einstein's theory, fits exactly mathematically with the cosmological constant, it's just way too small.
Right here.
Recent the speed of light.
Yeah.
However, that first graph that you showed indicated in the first, 10 to minus 32 of a second, there was very rapid expansion,
Right.
which would have to have gone much faster than the speed of light.
Well, but none of what happens in inflation violates the cosmic speed limit of the speed of light.
The question was about this observation of faster than light, the recent observation of faster than light travel, and whether
That's right.
whether
Whereas
inflation-
the recent observation of neutrinos traveling faster than the speed of light would violate the cosmic speed limit. So we're going to look very, very closely at those results, because the expectation is there's some subtle effect that hasn't been considered quite correctly.
The first expansion
Right.
was very huge, but
Right.
in a very short time.
That's right. That's right. And it's all of space. You know, it's not light moving faster than the speed of light in space. It's space expanding, right? Right. So what I'm told convincingly, and you know, this is now I'm getting on very thin ice, is that it does not violate the speed of light speed limit in that epoch.
Although the expansion was faster than the
Right.
right there, Al.
You have a simple explanation of what's happening to the entropy during these processes?
Ooh.
Total universe.
Question was, what's happening to the entropy of the universe during these processes?
No, I don't have a simple explanation. That's right. That's right. So we expect the entropy to continue to go up. I mean, the thing I always find most fascinating is that in many models we believe that the total energy of the universe is zero. Right? That we can, in fact, imagine creating a universe out of nothing, and that the gravitational binding, which is a negative energy, offsets all of the positive energy of the particles that are within the universe. So I found that already to be quite a remarkable structure. There are detailed arguments about the entropy, but let me not try to delve into those.
Hard to measure the entropy of the universe.
Right.
Maybe not. Other questions?
So you answered a previous question by sort of saying that space was expanding versus things were moving. But what's the difference between the space between me and you expanding by a factor of 2 in a second versus me just running sort of twice as far away?
Right. Well, okay, so let's see. So what's
Did
the
everybody catch
difference?
that? It was
Yeah.
okay. The
Go ahead,
question
say it
was,
again.
what's the difference between the space between the questioner and our speaker, between the space expanding versus him just running away very fast?
Yeah. So again, imagine the surface of the balloon with the dots on it, right? So if light is emitted from each one of those dots and grows as a moving at the speed of light shell, essentially expanding out, and in addition, the entire balloon is expanding. So the time it takes the light to travel from one point over to the next point is lengthened because you've stretched out space, and so it has to travel this longer distance, right? So you're not violating anywhere along that path information having gotten from one point to another faster than the speed of light. But that expansion can have occurred and push things way, way far apart. So it takes a long, long time for the light to travel back across that distance. Does that help?
Other questions? Question right there.
So on your plot showing mass versus cross-section, you
Right.
had different colors, I guess, representing different theoretical...
Yeah, and those all, the theories there are all like in these plots here, right? Right, these are all supersymmetric theories. They're usually called minimal supergravity, which are the most concrete possibilities for what makes up the lightest supersymmetric particle. And those are the most probable WIMP models that we know of.
So what are the different colors? And can you also say something about spin-dependent versus spin-independent?
Yeah, everything in this plot is the spin-independent cross-section. And the comment to make there is that all of the nucleons in a nucleus participate coherently in that type of interaction. So there is an enhancement for spin-independent couplings that goes as the square of the number of nucleons in the nucleus. The other type of interaction that's possible is a spin interaction, and those typically only couple to the one unpaired nucleon in a nucleus. So you need a nucleus that has an odd number of protons and or an odd number of neutrons. In our germanium case, one of the germanium isotopes, germanium-73, has an extra neutron, and so we have some sensitivity to spin dependent. And there are other experiments which go after spin dependent somewhat more. So that requires a different plot than the one I've shown here, but it's similar.
Question?
Question, when you're talking about the bullet cluster and how the ordinary matter separates from the dark matter, when they model that, are they assuming just gravitational interactions between the two segments, or are they...
They're assuming gravitational interactions for the dark matter particles and for the galaxies, because the galaxies have very small probability of hitting anything. And then they're assuming frictional drag between the gas clouds.
But is there any weak interaction between the dark matter and the dark matter, the two things?
There is, but because it's such a weak force, assuming it's zero pretty much leads to the same distribution as if you put it in. Because in other words, when those two move past each other, the local density of dark matter might double, but that's it. It only becomes twice as big, and the probability of annihilation is still very small. There are a very small percent of particles.
I mean, the weak force is stronger than gravity, right?
No. No, the weak force is stronger than gravity. It's very short range, okay, whereas gravity is long range. And so gravity keeps adding up to bigger and bigger.
Okay, well, I think we will decide that we've asked enough questions, and if people want to come up and take a few more minutes to ask Blas one-on-one. Otherwise, let's thank our speaker.
So,